Okay, so did you guys take a second to look at this one? What did we get for this one? Did you guys figure this out or no? 0.19, I heard somebody say. Oh, I didn't mark the answers. That's embarrassing. Do we agree with 0.19 or no? Yeah? Anybody disagree? Show how to do it? Okay, sure. Okay, so I guess the big thing here is figuring out what a kilowatt hour is, right? So $0.085 per kilowatt hour. Okay, well, what's a watt, you guys? It's a joule per second, right? So what we want to do is, sorry, my brain just totally stopped. Let me rework here. All right, so we let's convert this to what does it cost? Oh, there we go, 5 hours. I was looking for the time. That was what was messing me up. I didn't see the time. All right, so here's the idea. We know that our time is 5 hours. Okay, and the idea is they're going to charge us 8.5 cents for every kilowatt hour we use. All right. So why am I totally blank on this? All right. So we need to factor label here, and we need to convert hours into dollars, right? Does that make sense? Okay. Cool. Sorry, my brain is now on. I'm good. Alex, what do you got? You don't need to. That was what I was trying to get my head around, and I'm sorry I was being slow on it. So all we're trying to do, you guys, is convert hours to dollars. Okay? So, and what this information here is telling me, what this information is telling me is that 1 kilowatt hour is equivalent to $0.085. Good? So I'm literally just going to factor label. I'm going to multiply this by, man, what is wrong with me today? So we know the time. I know the power is 450 watts. Sorry.
Mr. Acker, what is factor label?
I apparently am having a tough time with it.
I don't know, what is it? I have no idea what you're doing.
Oh, do you guys not know what I mean when I say factor label?
No.
Oh.
Train tracks.
That's what factor label is. Same thing. You're changing, yeah. I don't know, that's just what I learned to call it. Okay. Wow, you guys, I am really sorry here. Okay, so look. So we've got 450 watts for 5 hours, right? So the work that we're going to do is power times time, right? Okay, so our power is 450 watts times 5 hours. So that's some number of watt hours, right? Does that make sense? All right. Times, there are 1,000 watts in one, oops, man. There are 1,000 watts in 1 kilowatt. So what units do I have now? Kilowatt hours, right? And then I can multiply that by, oh, well, $0.085 is the cost of 1 kilowatt hour. Cool? So, railroad tracks then. I guess you guys learned to do it this way. Railroad tracks. All right. What do you mean by what you had and what you had left?
Because you had kilowatt hours on like $0.085 per kilowatt hour. So that's on the balance. You just think kilowatts and hours now. Make the units cancel.
I got you. Yeah, and that's basically what I did. I started here instead of starting with I gotcha. Yeah, that works. All right. Wow, I did a rotten job explaining that. At the root of this, though, you guys, is work is power times time, right? Well, my watts are going to cancel from the top and the bottom of the railroad track. hours are going to cancel here. And then kilowatts and kilowatts. So we're just left with dollars, which was our goal, right? All right, are we good, you guys?
Yeah, we could do this.
All right. Wow, that was a struggle. All right. So, am I right? You get 19 cents?
Yeah.
All right, cool. Are we good?
Yeah.
All right. Wow. Okay. All right. Next order. Let's see. While you sleep, your body is using energy at a rate of 77 watts. How many food calories are used during an 8-hour period? 1 food calorie is equal to 816 joules. So again, railroad tracks, right? So we've got 8 hours. 77 watts is the same as 77 joules per 1 second, right? Good? So, the way that I would think about this is I would say, all right, well, my rate is in seconds, so let's convert our hours to seconds. Sorry, railroad tracks. So, 1 hour, 3,600 seconds. Good? Okay, and then this is telling me that 77 joules is the same as 1 second. So I'm going to put 1 second here, 77 joules here. And then we got to convert that to calories. And it says 1 calorie is 416 or 4,186 joules. So 4,186 joules is the same as 1 calorie. And I think all of our units cancel out, right? Good? All right. Is that not the way you guys are doing these? I feel like you guys are looking at me like, what the hell is he doing? Are we okay?
No, is a big C a coulomb as well as a cal of
Yes.
thousand?
To be honest, I've never seen capital C for calories. I've always abbreviated calories as CAL, but
Well, one is 1,100 calories. Other one's 1. Whatever.
So what the answer is C?
Yeah. End of the day, it's
oh, sorry. All right, are we good? Okay, everybody happy? All right, cool. So, somebody yesterday asked about 7.4 number 12, which was a concept you want, yes? So, let's dig out my sheet. For number 12. Okay, so number 12, it says the figure at the right shows 3 arrangements of a block attached to identical springs. So all of the springs in all of these drawings are the same. So drawing number 1 has 2 springs attached to a block. Drawing 2 is 2 springs, and 1 spring. And drawing 3 has 2 springs on both sides. Okay. It says rank the arrangements according to the magnitude of the net force on the block, largest first when the block is displaced by a distance d. So in A, we're displacing it to the right. Okay. So all right, so the only force acting on the object is going to be the force of the springs, yes? Does that make sense? And the assumption is that right now, all of these are at x equals 0, right? Okay? So all of these springs are the same, so that means they all have the same spring constant, right? So for any one of the springs, if you displace the spring either to the right or to the left, the force applied is just going to be k times the amount that you've displaced it, right? Okay? So let's assume that I push this over to the right a distance x. Good? Then what's happening is these 2 springs are going to push this way with a force of kx, but twice, right? Follow? Now, over here, when I push this way, these 2 springs are going to push that way with a force of kx. So that's 2kx. What's this one going to do? Same thing, right? Because if you compress the spring wants to uncompress. It's going to push this way, right? All right? So this one is going to have a force. This one's going to have a net force of 2kx. This one's going to be 3kx. And what's this one going to be? 4kx. Does it matter which way I displace it?
No.
No. This one on the right is always going to have the biggest force due to the springs when you displace it any distance, right? Because whether you compress it or stretch it, the spring still doesn't want to be compressed or stretched. And so it's going to exert a restoring force. Cool? So, so the answers for 12A and B, we're ranking them from largest first. So the answer to 12A is 3, 2, 1, and the answer to 12B is also 3, 2, 1. Good? You guys good, Marcus? You good, or you sure? Yeah. What's up?
Is it clear explain why they wouldn't like cancel out?
Because. So if how do I want to say this? All right. So this spring right now is relaxed. Good. If I stretch it this way, which way will the spring push? This way, right? Back to where it started from. Wait, am I wrong? Man. No, I was right. Yeah, right. Yeah, okay. Why am I struggling so much today? Oh, right. Yes. I'm sorry. Okay. Yes. So if I push this way, the force is going to be that way, right? Good. Now, suppose I've got. Sorry, that's what I was. Suppose the spring is this way, and I stretch it that way. Now, which way is the spring pushing? Still this way, right? So no matter which side the spring is on, if I displace the object that way, the spring is going to want to restore it and push back the way that it came from. So all three of these springs, if I push the object that way, all three of the springs are pushing back this way. Well, two of them are pulling and one of them is pushing. Cool? All right. Okay, are we good? All right. Okay. All right. Now it says rank the arrangements according to the work done on the block by the spring forces. Greatest first when the block is displaced by distance d. I think it's going to be the same thing, right? Because the work done by one spring is 1/2 kx squared, right? So we're going to have 2 times 1/2 kx squared, 3 times 1/2 kx squared, and 4 times 1/2 kx squared, right? So I think all of the answers are 3, 2, 1, right? Sorry? Because x squared is going to square out the negative. Right?
Isn't it 1/2 ki squared, x squared minus?
Oh, I got you. Yeah, so technically it's I squared minus, I got you. I see. Does it say magnitude? Yeah, it says magnitude.
Oh.
Actually, no, it doesn't.
No, it doesn't.
Doesn't.
That's why I said 1, 2, 3 for negative.
You're right. I agree with you. I agree with you. It doesn't say magnitude, so you're right. Technically, all of these works are going to be negative.
So it's 1 has the least negative.
Right. Right. You're right. That's worded sloppily. What? Just out of curiosity, what does the answer say on the thing I posted? Anybody look? It says 1, 2, 3? Okay. Cool. So yeah, you're totally right. The negatives do matter. So the idea is, so let's look at this first case. It's the easiest one, right? If I stretch the spring this way, then my displacement is this way, but my force is the opposite direction. So the work is, so what my initial x is 0, right? So my work is actually 0 minus 1/2 k x squared. So all that Alex is saying is that the work done by the spring is going to be a negative value, right? And so even though technically this is sort of the biggest change in energy, it's losing energy, so it's a negative amount of work.
Why would magnitude lose magnitude? Why would change?
Because magnitude doesn't include direction, and so then you're basically just getting rid of positives and negatives. Good? Everybody good? Okay, cool. Thank you for pointing that out, Alex. All right, is everybody good with this? Yeah, Ethan.
Number 3, so you move it a distance of d. Say it's positive. When the force of those two strings make a negative force, the force of the other strings make a positive.
No, that was what I was explaining to Christian. That if I suppose I push,
I get that, but like, oh yeah, okay,
so suppose I push it over to here, right?
yeah, I get that. But
So my displacement here is positive, right? But all 4 springs are pushing in a negative direction. Good? Everybody good? Because the springs are working against you trying to move it that way. Are we good? Okay, cool. This is why it's important that we go over these concepty things, because but knowing this stuff is going to help you with problem solving too. Yeah.
number 1, we push it that way, the distance be negative,
And then what? And then the force would be positive, right? Yeah. So that's why Hooke's law is actually, or no, that's not what I want to say. Yeah, that's why this was initial minus final instead of final minus initial. Okay, cool. All right. Are there other concepty ones that were jumping out at you guys from any of the sections? We've got tomorrow, so we can do other problems tomorrow too, if you guys want. Yeah.
You do 11 on 7-6.
11 on 7-6, concepty one. Like questions? Gotcha. All right, so here we go. 7.6, number 11. Holy cats. Ugh. Smartboard is not cooperating today. All right, it says in 3 situations, a single force acts on a moving particle. Here are the velocities and the forces, and then they give you a few scenarios. It says rank the situations according to the rate at which the energy is being transferred. The greatest transfer to the particle ranked first, so that would be positive power, right? And greatest transfer from the particle, so negative power, ranked last. Okay, so here are our choices. So number 1, we know that our velocity is negative 4I. I'm going to skip units for the sake of time. And that our force is 6I minus 20J. Okay, so how do I find the power down there, you guys? Like, what's the equation using this to find the power at that instant? Yeah, it's FV cosine theta. But what is that FV cosine theta? What's that? What are we doing when we do that? Dot product. Okay, so do you guys remember from you multiply the components and then add them, right? So for this one, power is F dot V, which for us is negative 4 times 6. I shouldn't do dot there because that's going to be confusing. It's negative 4 times 6 plus, what's the J component here? 0 times 20, right? So you're going to get negative 24 watts, right? In other words, this thing is losing energy. Make sense? All right. So then you kind of go through the other ones in the same way. I think they're all written as unit vectors. Yeah, unit vector notation. So number 2, we get the velocity is 2I minus 3J, and the force is negative 2J plus 7K. So what's my power there going to be, guys? 6, right? There's no I components, no J components, right? So it's just, I'm sorry, no K components. So it's just going to be the J. So my power here is going to be 2 times 0 plus negative 3 times negative 2 is 6. And then 7 times 0, right? So you get 6 watts on that one. Sorry, the calibration on the board is going, so my writing's going to get worse as the hour goes. Yeah.
there isn't any like cross product in this chapter, right?
Correct.
It's just the only dot product going to be.
When we get to torque, it's cross product.
It's just the only dot product.
No, work is force dot displacement. Good, you guys? Okay. All right, and then number 3. Let's see, number 3, the velocity is negative 3I plus 1J. I added in the 1 on my own. And then the force is 6I. No, it isn't. 2I plus 6J. All right, so what's my dot product going to be there? Let's see, we're going to have negative 6 plus 6, so 0, right? Follow? So I think we're going to have 2, 1, 3, right? Because this one is positive, so that's our biggest. 0 is bigger than negative 24. So 2, 1, 3. 2, 3, 1. Sorry. Yes, I said them right. I just said that. Yeah. Cool? Oh, no? Okay. Questions on this, you guys? Yeah.
When you do the dot product, you get negative 6 plus 6. Isn't it I and J? I don't understand why you add.
So that has to do with the definition of dot product.
So you do it.
So I dot I. So what's the magnitude of the unit vector I? 1, right? So what this really means is, remember, so like A dot B is really A times B times the cosine of the angle between them. So I dot I is the magnitude of I is 1 times the magnitude of I is 1 times the cosine of what's the angle between I and I? 0. So 1 times 1 times the cosine of 0 gives you 1. Okay. Remember, when you do a dot product, yeah, good luck. When you do a dot product, you end up with a scalar. Okay. Does that make sense, or?
That's I times I. What about I times J?
Oh, that's the point, though, is that they don't matter. So negative 3I times 2I is negative 6 times I dot I. But I dot I is 1. So this literally becomes negative 6 with no i's, j's, or k's. Same thing over here. Follow? So when you take a dot product of two like unit vectors, I dot I, j dot j, or k dot k, you get 1. Follow? And then what's I dot k? 0, right? Any two unlike unit vectors, the dot product gives you 0 because they're perpendicular. Good? Okay. Any problems with whatever number that was? Okay. Were there any of the concepty ones from 7.5 that we wanted to talk about, I guess, while we're on this sort of concepty roll? Oh, no, there weren't. Oh, you know what, though? I realized after I gave these to you guys. So on the 7.1 worksheet, a couple of those graphs I probably should have put into section 7.5. So I guess I would just say, maybe tonight, go back and look at the concepty questions from the 7.1 worksheet and make sure you're good with them. Because there's a couple sort of weird things about some of those problems, and I was surprised nobody asked about it before. Okay, so look at those tonight and see if you have questions on it for tomorrow, all right? Good. All right, which problems do you guys want to look at? Yeah?
I just have a general question.
Yeah.
Love the graph they gave us at 7.5, where instead of position versus forces, so to find like the area of the curve, is it always going to be okay to just take the area of the curve of the acceleration graph and then multiply by the force?
Yeah, because your acceleration is proportional to your force.
Yeah.
So, I mean, you could rescale that acceleration axis to be force just by multiplying through by whatever your mass is. So, yeah, you can totally do that. Really good question. Really good question. Yeah, you're right. There's 2 of them like that. Sure. Oh, yeah. So a couple of people are asking about 42. So, there's 2 ways of doing 42. All right? Option 1 is to do it using an integral, and it gets ugly, but it totally works. All right. Then there's a super secret ninja shortcut you can take, which works. And some people were asking me about this during the tutorial today, and I have this sort of let me just do it. I am foolishly going to try calibrating the board one last time. I've restarted my computer once already today, but every once in a while it just, I think the smart board's ready for break too.
It's on break.
All right?
It's on break.
It's on break. It might be. Okay, so here we go. One last time. All right. So the issue is this. So, is it going to keep? I don't know. We'll see. So here's the pulley. So the idea is you're pulling the rope over here with some amount of force, right? Creating tension in the rope. The pulley redirects that tension so that the tension acts up. Oops. So the tension acts up at kind of a weird angle, right? So, but the problem is, as your box moves from position X1 to position X2, I keep doing this. I really need to get in the habit of not being sloppy about where I put my X's. As the box moves from X1 to X2, that angle is going to get steeper, isn't it? Right? And so the issue is my displacement is this distance. The force doing the work that we care about is really the horizontal component of that tension. Right? Now, we know that this tension is always 25 newtons, right? But when you bend it at this angle, the horizontal component's always going to change, right? Because the angle's going to change. Does that make sense? I'm sorry? Yeah, so it's totally a related rates problem. So there are two ways of doing this, all right? Option one is to write an expression for the x component of the force of tension in terms of this height which you're given, x1, x2, and the given force, 25 newtons. And then integrate it from here to here. And it works. The integral's a little messy. All right, and the conversation I was having during tutorial is that a lot of you guys haven't really done that much integration yet, so you're not super comfortable with it yet. Okay? So that way works. And I'll be honest with you, when I wrote up my answer key, that was the first thing I did. Okay? Then I went back and looked at the solution, and the solution that's in Halliday-Resnick is a gabillion times easier, and as soon as I saw it, I was like, oh, that works. Why it works is a little tougher to explain. All right? So, but here's the gist of it. Remember, you guys, this pulley is really just redirecting the force, right? When I pull the rope, I'm pulling it with a force of 25 newtons, right? But the amount of rope that I'm going to pull is going to end up being more than that distance, right? Because the pulley is causing the rope to bend a little bit, right? So we're not pulling it in a straight line, right? So if we can figure out the distance over which we pull the rope, then you literally just do force times distance. Does that make sense? All right, so the question is, how much rope do we pull out? Well, all you got to do is this. Look, there's two triangles. Triangle number one is this. I know x1. I know my height, so I can find the hypotenuse, right? So find the length of the rope there. Let's call that L1. Do you guys agree we could find that just by doing Pythagorean theorem?
Yeah.
Okay. Then, when the box gets to right here, there's a new triangle. Oops, I wanted that to be red. There's a new triangle. Why do you hate me? There's a new triangle. We can find that length also, right? Just subtract them, right? Because that'll tell me how much rope I pulled out. Make sense?
Yeah.
And then just multiply by the force, and you're done. Right? Because the difference between these two lengths must be how much rope I pulled forward, right? Because whatever rope's not down here must have been pulled out up here.
So how to do? Yeah, we see the hard way.
Before I do, does this make sense? What's wrong, Alex? Where'd I lose you?
Wouldn't you have to find the horizontal, like the blue bottom of the triangle to find out how much rope?
Well, you know it. Well, yeah.
No, you're talking about the force, not the... You're talking about the force triangle, not the displacement triangle, right? Is that what you're talking about, Alex? So, we know this is a position of 0, right? And this position is, what is it? What's the starting position? 3 meters? So we know this length is 3 meters. We know this is 1 meter. So we can find this blue hypotenuse, right? So when you start, that's how long the rope is. You good with that? I'm not done, but are you good up to there? Okay. So then you pull it forward, and eventually the box gets to here.
Okay.
And so now you've got this other length of rope. So the length of rope goes from whatever L1 is to whatever L2 is. I don't know what it is, but suppose it turns out to be, whatever, 2.5 meters, right? Well, that means that I pulled out 2.5 meters while exerting 25 newtons of force. So multiplying that gives you what what the work is. It's good. It's not 2.5 meters. Okay. Yeah.
I did think it was like the whole meters.
Yeah.
It's just off. The decimals in the wrong spot.
Oh, is the decimal in the wrong spot?
It just looks like you were typing too fast because you put the decimal.
Oh. Yeah, you're totally right. That's another point. Yeah, it is. It's 41.7. Yeah. What number is this? 7 point.
7.542.
Number 42. Okie dokie. All right. All right. So the other way of doing it is by taking an integral. Do you guys want to see this?
Yes.
Okay. All right. Let's do it then. I am going to clean up the board a little bit then. Okay. So check it out. What's wrong, Mary?
I said I don't really want to see it. I think it's just going to confuse me.
Oh, really?
I'll just keep chugging away at my homework.
So eventually you guys are gonna have to be comfortable enough with integrals that you can do this.
That's why we're at
It's funny because in calc, whenever we get a physics problem, I just solve the kinematics equation.
Yeah.
Because whenever I'm given a problem that I can solve just using calc, I do it that way, easy calc.
That's funny. So you're like, okay, all right. So suppose that the box is at some random position. Let's just call it X. Okay. So what I'm going to do is I'm going to write an expression for, the idea is my tension force is going this way. I'm going to write an expression for the horizontal component of that tension force in terms of this value of X. Okay? So there are two triangles, and the trick to this is that the two triangles are similar. So you can do it using trig if you want, but it's way easier to do it using similar triangles. Okay? So the two triangles that are similar are your force triangle, force of tension in the x direction, force of tension in the y direction, and your displacement. Displacement's not the right word, but like your length, your distance triangle, right? The idea is horizontally, this rope is going to stretch a distance of x. Vertically, it's a distance of h, right? And then this L is the length of the rope, right? Where L is x squared plus h squared square root of 5. Good? Everybody good up to there? All right. Sorry? 1.2. Oh, gotcha. Yeah, it's the distance from the fillet down.
Does it matter?
It does matter, but the drawing on the worksheet shows it correctly. Cool. So it's showing from where the rope is connected up to the top of the rope. All right, are we good? All right, so I want to write an expression so remember, our known value in this triangle is the force of tension, right? And I want to write an expression for the x component in terms of that and h and x. Follow? So I'm going to write the following equality. The force of tension in the x direction is to Fx. Nope, sorry, is to the tension force. In other words, the horizontal part is to the hypotenuse as the horizontal part is to this stupid square root. Does that make sense? Does everybody understand that those two triangles are similar? And does everybody understand that we can then set ratios between sides equal to each other like that? Okay, cool. So multiply both sides by Ft, you get this. Our force of tension in the x direction is going to be our force of tension times x. And instead of writing divided by the square root, I'm going to write this as times x squared plus h squared to the negative 1/2 power. Follow? And keep in mind, we know everything in here on this side except for the x, right? Because that's what's changing as the box slides, right? Follow? Okay, this is a really good example of a good use of an integral. Okay, so now what we want to do is the work done by our force, because our displacement is horizontal and our force is horizontal, our horizontal force is horizontal, we can just multiply those, right? So our work done is going to be the integral from a position of 3 to a position of 1, right? Of the force of tension in the x direction. I got to manufacture a negative sign to indicate that this force is also to the left, so I'm just going to stick a negative sign there. The other option is to, instead of integrating from 3 to 1, to integrate from 1 to 3, and then get rid of the negative sign, and that works too. Is that what you're asking? Yeah, and that totally works. Oops, I forgot my I wrote that wrong. Force of tension in the x direction with respect to x. Sorry about that. Are we good or no? Okay, so here we go. This is the integral, the negative integral from 3 to 1 of this mess. Force of tension times x squared plus h squared to the negative 1/2 dx. All right, so we got to undo the chain rule here, kind of, right? So somehow this exponent became negative 1/2. So before we took a derivative, what was that power? Positive 1/2, right? So what I'm hoping this will do, I'm hoping that this is going to be, what happens if I take the derivative of that? Do you see why I started here? Right? So when I take the derivative, oh, so I still need to, I need that tension force to be in there, right? Okay, so hypothetically, if I was to take the derivative of this, what would happen? Let's see. This is a constant. I would bring the 1/2 down out front, right? Reduce the power by 1/2, so that takes care of that. But then chain rule says you got to take the derivative of what's on the inside. So what's the integral derivative of what's on the inside? 2x, right? So I've got 1/2 times 2x, which gives me x. What about the h? Good question. Why am I not worried about the h? Because it's constant, right? The derivative of constant is going to be 0, right? Oh, sure, yeah, you could 100%, yeah. I'm trying to get in the habit of solving problems and putting the numbers in last, so you guys get used to seeing the Hitler thing. Oh, there's no numbers? We're solving this with no numbers, right? Okay, so I'm going to try to do this as much as I can and not put the numbers in until the end.
So technically you could have put 25x times x squared plus 3 squared.
100%, yeah. Yeah, sorry, I'm just grabbing one thing for Will here real quick. All right, yeah, Marcus. Oh, no, not at all. I can only just do this. All right, so are we good up to there? All right, and then, oh, I forgot my negative sign. And then you evaluate it at 1, evaluate it at 3, and then subtract. Cool? No, because when you take the x came out because when you take a derivative, you're going to go 1/2 of x squared plus h squared to the negative 1/2 times the derivative of all of this, which is 2x, right?
Oh, okay, no.
Right, but so we're sort of, when you take an integral, it's an antiderivative. I don't remember who was that asked that the other day, but good? All right, now, your math teacher is going to teach you a way better way of doing these integrals, and I learned it at one point, and I honestly don't remember what it is. I need to review it over the summer. I just kind of do it by looking at it and thinking about it, which is sloppy. So I apologize. It's on my list of things to do. There's like a more technical way of doing this. I think they're probably going to teach you to do it using using substitution, I think. Okay? Sorry? Substitute U in, right. Yeah. So I haven't done it that way in so long because I just sort of do it, you know? All right. Okay, so. All right, so to finish this, here's all I'm going to do. You plug in your numbers, right? So I'm going to get negative, let's see, our FT was 25, X, oh, sorry. Let's see, so my X is starting at 1, so I'm going to do 1 squared plus, my height is 1.2, is that right? To the 1/2, right? Minus the same thing if you evaluate it at 3. So negative 25 times 3 squared plus 1.2 squared to the 1/2. Close your parentheses. That should give you whatever we said, 41.7.
Alright.
Yeah, Mark.
Okay, so I get like the work and equals like the integral of x and substituting. I don't get the strength from the most. So
From here to here?
yeah.
Yeah, and that's kind of the problem with this, is that you guys haven't had a real good exposure to integrals yet, which is the conversation we had in tutorial, so that's kind of why the other solution is better. You know what I mean? That first solution I showed you?
Yeah.
Because then you don't have to take the integral. So here's how I think of integrals, you guys. I always just think, what thing do I need to take the derivative of that will get me what I started with? Okay? So my train of thought was this. I started out with this thing, ft times x squared plus h squared to the negative 1/2 power, right? So I took the derivative of something, some mess, and I ended up with this, right? Okay, well, I know the power rule tells me that when I take the derivative of something to a power, you move the power to the front and then reduce the power by 1, right? So assuming I followed that rule here, what that means is I must have started with x squared plus h squared to the positive 1/2 power. Because then when I bring the 1/2 down and subtract 1, that gives me negative 1/2, right? Good?
Yeah.
Okay. So when I take the derivative of this, I'm gonna bring a 1/2 down, right? But you also have to take the derivative of the inside, right? Because you got to do chain rule. So what's the derivative of this inside? 2x. And then the 1/2 and the 2 cancel out, so that gave me the x that I was looking for, right?
Yeah.
And then you got to put the ft in because that's your constant. Cool? All right, we did not get through a ton of these. So tomorrow, come in with other questions. Real quick, my goal is to keep this test short. I'm thinking probably just one free response question, like literally one free response question. And yeah, like 10 multiple choice questions. I feel like this really is only half of the chapter anyway. Okay, because there's still potential energy. So, there you go.